let's see.
If it really doesn't work, oh, there.
Yeah, here we go. Yeah, it was weird that it shared and I hadn't done that. So anyway, let's just, so this is our brand new stylized ESCI climate risk assessment framework, which has gone through a few iterations. I think everyone's sort of been used to seeing those green bubbles going around. So this one is sort of like more focusing on what ESCI is actually doing, where the green bubble framework, we were only ever doing the first 3 bubbles anyway. So this is much more focused on ESCI and what we will be working on. So all the risk assessment frameworks will, we advise that we'll pass through this kind of process from, we start off, and I am going to show you the 3 different case studies and follow this sort of process each time to sort of, so you can kind of get the idea of what we're doing. And anyone can interrupt or ask questions as I go through. All right, so first we need to understand the context of what we want to know about, you know, like, then once we understand the context, then we have to identify how that sector or asset might be exposed to the climate in an historical sense, right? Next step is to look at all of those different iterations and all those different aspects that Michael has introduced. We do integrate into these climate risk assessment frameworks. So I'm going to be spending a bit of time on what Michael has explained to you as how we introduce that into undertaking our study. Finally, we look at the evaluation of the climate risk. So how the projected climate might actually impact on our asset or our supply model, for example. And then finally, what we might do to mitigate or adapt. So you'll see this framework dotted all on every slide, so to help you understand where we are in the steps. So the first case study I'm introducing today is one that was brought to us. Jill's actually on the line, so Jill, I'll be introducing where we're up to, because we're still in discussions on this case study we're undertaking for the distributed energy resource systems, DERS, where we're looking at the feasibility of introducing SAPs as standalone power systems into a community. All right. So in this case study, and the context of the case study is, we want to make sure that we increase or maintain power supply reliability to isolated townships in Australia. All right. So for that, we want to assess the future feasibility of these, what's known as standalone power systems. I'm pretty sure everyone on the call knows what these are. Yeah. So there are all these like solar, battery, solar, alternative power supplies, okay, to the actual gridded power, or the power supply that comes in on high voltage power lines. So it's off grid, okay. So what we want to know is, will power outages increase in future if bushfire frequency and severity increases? So in this lovely schematic, I think it's really nice that the schematic that was provided in the assessment sent to us, that was undertaken by Cutler Merz. All right. So you can see here, this is the before, where there's this high voltage feeder going through to a community and it's generally a smaller township. All right. Or the after, where this smaller township is then not relying on the feeder at all. It's relying on this standalone power system. So this is the context of our risk assessment. In all of these risk assessments, I hope all of you are thinking of how this might relate to some of the questions you might have for whatever you're involved with into the future. All right, so just think about, how is what my problem will be, or what I'm being faced with, how does this fit into this framework, right? Oh, and as I said, Jill, I've been working with Jill and other colleagues on this particular case study. And we're actually only at the point where we're analysing the climate risk. We haven't done any evaluation or risk treatment, but I thought it was a really nice way to introduce this risk assessment framework, because it's a really interesting problem that they're looking at. So here we go. So let's identify the climate risk. We've got this power going to isolated communities. And the question is, have you noticed any changes already? And in this case, yes, because power supply got cut off to this community, right? So there's been changes. The question then comes along, are the changes related to climate? And in this case, yes. So what's been happening, and think of, for example, Malakuta last year, where fires come through a forest, and that cuts off the power from the high voltage feeder and into the, so the town does not have its power supply anymore. So yes, what we want to, so the climate factor that's related to this power supply cutoff is forest fire, okay? So if you see on the right here, this is in this little panel says identify climate risk. First is identify the historical relationship between the impact and the weather and climate. In that case, in this case, it's the fire. But also there's often literature that you can access or other types of information, for example, engineering standards. So this is the point in a case study where you start to do a review of what we already understand about this type of situation. Okay, so also in regard to analysing the climate risk, we look at, where possible, how to quantify the assets and systems and the services that are likely to be impacted by the future climate. So in this case, we want to understand what the range of future change in fire risk and how that will be, how that will affect the feasibility of standalone power systems, okay? Noting I use the word range there, and all of you are immediately thinking of, oh, okay, to assess the range of future change, we need to look at all of those things Michael spoke about, like the different modelling outputs and also the different emissions pathways into the future, because we want to understand the risk at a high impact risk and the lower impact risk to undertake this assessment and to try and gauge the range of potential adaptation strategies that we might have. So this is important factor in this particular case study. So, okay, now we're up to the step 3 in analysing the climate risk, okay? So we have to choose appropriate climate information and data sets. First thing we need to know is what time frame are we interested in? And in our discussions with our team of people that are working on this project, Jill, correct me if I'm wrong, I think we decided that we're going to look out to 2050 to see whether or not what the fire danger might be at that point in time compared to what it is in the current point in time. So 50 years was how we thought we would be. That's our planning horizon for this particular project. Some projects, and maybe it is relevant for this one, might even be a further planning horizon out to 2090, for example. It's just something to consider when you're planning this kind of project, risk assessment. Okay, so choosing appropriate climate information and data sets, and Michael went through this in quite a lot of detail earlier. We need to know that there's a lot of climate scientists used to use the word uncertainty, but we have to move away from that, because it's not uncertainty, it's because of the range of results, the range of change into the future, okay? So for example, as Michael said early, in the early period, there is a lot of uncertainty due to the internal variability in the climate, and through to the later period. I'm looking at the temperature in June, July, August. This particular, so through to later, if we're looking out to 2050, for example, it's important to start to consider, because of the scenario uncertainty, it's important to consider perhaps looking at two different types of emission scenarios or emission pathways, and also to consider the range of climate models, given that there is that does integrate into the fraction of the total variance in this time frame. All right. Michael explained this so much better. Hopefully, between Michael and me, you guys have an idea of what these schematics mean.
I think you did a good job. Yeah, no, I think you did a good job, Leanne. Yeah, totally. I think another thing to just mention again and again is just like how big the yellow fraction remains. Like climate change isn't about like we've got a really clear pathway which we narrowly stay on. Like climate variability is big in Australia and in a lot of places. And what happens over the next 20 years will really depend on, like, if we get a couple of big El Nino events, we get a La Nina-like period for 10 years, that kind of thing. And people have got to get that expectation right in their head. Like, it's not this kind of narrow path we're kind of following. We're changing the odds for sure, but there's always a lot of variability decade to decade. And you see this play out in things like, say, the supposed slowdown of global warming in the 2000s, and people were making a big deal about this, temporary slow trend in global warming, whereas people were just pointing out, of course you expect that. You expect variability, and sometimes it offsets the longer term trend, sometimes it enhances the longer term trend. And climate change tells us about the shifting odds, but there's still a lot of ups and downs and variability along the way to determine what we actually experience. Yeah.
And has been played out in last summer compared to this summer in this part of Australia as well. It's quite different. So yes, thanks, Michael. Okay, so looking at the variability, the green, the scenario uncertainty or the emissions pathway uncertainty. Oops, sorry, that way. What we need to consider, and Michael's explained this really clearly already, is a range of emission pathways into the future. So for this project, we've decided to use the pathways, the 4.5 and RCP 4.5 and RCP 8.5 emissions pathways into the future. Noting that they will, by 2050, the 4.5 and 8.5 will still will have a bit of a different impact on the temperature change by that period. Way more so towards the later part of the century, as we've explained. Okay, so here's another diagram showing some climate models. So this is the as we say, there were 41 CMIP5 GCMs in the suite. So CMIP5 couple model intercomparison project that Jill asked us to describe earlier. So it's just where everyone, all the climate modelling groups around the world enter their models, or they put their models into this intercomparison project, and they're all compared, and so we have access to all of those different models. This one here in these two diagrams is the Access 1.0 global climate model, and that happens to be the one that was produced by SARO and the Bureau of Meteorology. Okay, so, and this shows on the left that by 2050, under the high emission scenario, the projected average annual rainfall change, where blue is, oops, oh, sorry, I'll turn my phone to silent. sorry about that, where the brown is getting drier and the green is getting wetter. So as Michael said earlier, a lot of models are agreeing on that drying in the southwest Western Australia, and you'll see that in the next slide as well. On the right-hand side, we've got the Access Global Climate Model 1.0 by 2050, the temperature change, and you can see across Australia, it varies regionally, with warmer in the area in Western Australia, and less warming, but still warming in the eastern part of Australia. Now, remember these two models, because I'm going to flick the slide forward. So the Access one's in the top there, but this is the range of 8 different climate models chosen to represent the projected change in Australia. On that bar plot that Michael showed earlier, they were the actual different icons that represented the range of change, in that case for Eastern Australia. Okay, so these are the different models. So the Access is one of them that you just saw, but have a look at the differences in the rainfall change. So you can see some of the models are showing much drier. Some of them are showing much warmer. So if more pink is more warmer, for example. Okay, so there's a range. So what we could say is we could pick out of all of these 8 models, we could pick, say, the most dry, warmest model and the least warming and to the wetter end of the modelling to get the range of potential impacts into the future. All right. So this is how we as climate scientists, what we do is we go through the process of selecting the different climate models, just like what I've shown you just here, to represent a range of change for your particular region. All right. So in this case, the best case model would be the NOR ESM1M model. A lot of jargon in this. I'm sure you guys all have a similar sort of jargon. And the GFDL ESM2M model. So this is worst case, best case. So that's sampling the uncertainty associated with the regional modelling. All right, so that's the second source of uncertainty. So there was variability, climate variability, regional modelling uncertainty, and then the emissions uncertainty. So we have to take into account all of these 3 things when we're conducting a risk assessment. Oh yeah, so again, this is that same slide showing the different models. I think the square, actually that's the CAN model there. I think the GFDL is the triangle, but you can see all the different models as they lay compared to each other, the 8 models, as they lay among the results from the actual 40 different climate models that were represented in this assessment for Eastern Australia. Okay, so back to our case study. So, sorry, just seeing where I'm up to here. So we're analysing the climate risk. And here we see we're going to interpret the range of change. This is what we're deciding on at the moment. The team that are undertaking this case study, we're doing a range of change. We're looking at the Forest Fire Danger Index as a metric, and I'll discuss that a little bit more in a minute. Future projections under 2 different emission scenarios, 4.5 and 8.5. A range of climate models that we will select, just like exactly like what I just showed you in that past set of slides. But we'll also, and for that range of models, we're going to look at different time series results and also gridded data sets. All right, so going back into the assessment, so where possible, quantify how asset systems and services are likely to be impacted in future climate this is back to that the report that was done by Cutler-Merce on the feasibility of standalone power systems. And here, looking at the benefits and the costs of introducing a standalone power system. So there's a lot of work already been done in this space, noting that if you add all the benefits and then subtract all the costs, you end up with a negative $8.6 million. So it's going to cost $8.6 million overall to undertake to introduce standalone power systems into this community, as was done by this reporting. Of course, the avoided costs of things like post-bushfire line rebuild, for example, or you don't have to do all the maintenance on the forest around the trees all the time. So they're the avoided costs. They're the benefits, and the avoided costs are the costs. Sorry, are the costs of the standalone power system. Also, as a part of this study, and thanks, Jill, for helping me understand this a lot better. So this is the base case where the cost is $8.6 million. But then what they've gone and looked at the sensitivity of this case study as it's sensitive to different parts of the contribution factors into the case study. Okay, so for example, if the high voltage feeder to rebuild cost, rather than the estimated, say, $50,000, if it costs $200,000, the feasibility for introducing this standalone power system is actually in a positive territory. Okay. Similarly, with bushfire probability, they've assumed in this case study a probability of 4% occurrence of bushfires is in this probability. But if the probability of bushfires increases to 10%, it also pushes the benefit to a positive territory. So if the incidence of bushfires increases, it becomes beneficial to introduce standalone power systems. And this is the important part of this case study. If under projected climate conditions, the bushfire risk increases to a certain level, it means that it is worthwhile investing in standalone power systems for this certain community. So this is the point of the case study. We need to understand what the current risk of bushfires is in a certain region, and then the future risk, to see whether or not it increases feasibility for undertaking this assessment, or undertaking this investment, excuse me. Right now, and this is where the point we're up to in this case study, and we're currently looking at the literature and we're looking at the different data sets that we have available. We're right now trying to understand how we best define current risk and future bushfire risk. So this is an ongoing assessment. But to date, this is what we have to hand, is we have some time series. So these are projected time series for what this is in. I'm just showing here one particular climate model output, and for 2 example years of daily forest fire danger index. Okay, so this is for Traralgon, I think. Yeah, Traralgon for 2019 daily forest fire danger index and these are the different months of the year. All right, through to December, January through to December, showing that in January in 2019, modelled climate in January 2019, that the forest fire danger index will, in some cases, reach 50, which is seen as a bit of a threshold value for indicating more severe bushfire weather. By 2056, the bushfire forest fire danger index is actually above 25 in way more cases, So that's another threshold value that's used in the industry in understanding forest fire danger risk. But even in one situation in 2056, that's above 75. So that's a very high risk day. So what we can do is in future, we can look at these different time series of forest fire danger index. We can also look at gridded data sets showing different levels. This is forest fire danger index of greater than 50 across Australia to sort of show us where some of the most changes might be taking place. I was not involved in this particular case study, but it certainly goes through the same steps that we're encouraging anyone that is undertaking a risk assessment. The same steps were taken in this particular case study, the wind farm heat case study. Okay. Oh, it's going to have why is it doing that? It's not letting me change again. All right, I'm going to do that again. Oh yeah, just have to remind it that it's in that version. Anyway, so the context of this case study is we want to know how will wind farms be affected in a warming climate. All right. And wind farm output is predominantly a function of wind speed, but we want to know if heat also does have a role in that. So that's our question. So what this is, in order to understand the context, we need to ask the question, have we noticed any changes already? And this is a day in the case of this particular wind farm, showing the black line indicating the wind farm output across the day. The blue line shows the wind speed. The scale for the blue line is on the right-hand side there. And the red line shows temperature. Oh, actually, this is wind speed and temperature. So this shows, and so you can see when temperature exceeds a certain threshold, the wind farm output goes to 0. So what we're seeing here is that wind farm is affected by high temperature. Okay, so we're in understanding this is understanding the context and identifying the climate risk. So the context is wind farms are affected by high temperatures. So the aim of this assessment was to understand, well, how will wind farms be affected into the future with warming temperatures? So the people involved in this case study looked at this modelled wind farm output. So this is 2 graphs, one laid upon the other one, with the black circles indicating the normalised power coming. So one is that it's operating at a very efficient, and then the efficiency of this operation is indicated in this left-hand axis. So this is 40% efficient, for example, 0.4, where one is it's operating at its capacity. All right, and you can see that this is the modelled wind farm output. All right, or the power output is indicated by these lines with the different colours indicating the different temperatures at the ground. So when it's 20 degrees, the purple line shows that when the wind speed gets to about 20 metres per second, it's operating at full capacity. All right. Let's follow the 40-degree line, this green line. So if it's 40 degrees, the wind speed's increasing, and then you can see here at 40 degrees, it only really gets to 80% capacity. When it gets to 42.5 degrees, even at 20 metres per second, the capacity is only 60%. So what we're seeing is that the wind farm output is definitely affected by warming temperatures in this modelling assessment. And this is the sensitivity. Oh, I didn't mean that. This is the sensitivity curves for under all of the different temperature thresholds that were produced in this modelling study. Okay, so this is the climate risk, is that high temperatures have a negative impact on wind farm output. Okay, so what are we going to do? In this particular case study, they weren't interested in the range. They just want to know what the worst case is. They just want to know, they're stress testing the wind farms to see by when the capacity or the output from the wind farm will be impacted. So they only were interested in looking at the hottest climate model under high emissions. And the other thing they were also interested in looking at is the probability of exceedance data, which shows the actual maximum temperatures, like 1 in 10-year hottest temperature that will occur in a gridded format across Australia. So you can see here, this is some examples of probability of exceedance data output showing this is the 90th percentile, so the hotter range of models, all right, that are used in this to produce this data set, through to the cooler range of models. And this is the middle of all the modelling output for the 1 in 10-year hottest day, okay? So here is what it's like in a historical climate, and then by the 2030s, and this is the 2050s, all right? So this is if you're interested in threshold data or exceeding thresholds, we have these probability of exceedance gridded data sets that you can access as part of the ESCI suite of products, all right? The other data they access for this case study is a 30-minute time series data set that has been prepared with some of the downscaled modelling output that Michael has described to you. It needed to be downscaled because the temporal resolution of most of the global climate models is, we usually get monthly climatologies out of those. And you can get some daily climatologies out of the global climate models, but not sub-daily. So we've used downscaling techniques to provide 30-minute time series data. And this might be important for if you're doing this kind of wind farm modelling, or for example with supply and demand modelling that AEMO is mainly interested in. So in this particular case study, we looked at the 30-minute time series data from 1980 through to 2060 to run this wind farm model. Okay, and so these are the types of data sets that you would use if you were stress testing or looking for worst case outcomes for an asset, for example. Hottest model, highest climate scenario, emissions pathway. And this is the results. So when they were evaluating the climate risk, they found that the average capacity factor through the period of time, on average, didn't seem to be negatively impacted. Though when they looked at the wind farm capacity factor on the top 3 hottest days, looking into future climatology, there was a definite decline in capacity factor. So this is a really hot climate model under high emission scenario. And these downscaled CCAM simulations producing 30-minute time step data sets. So that's some of the other types of data sets you might like to access depending on the type of study you want to undertake. And I know there's a few AEMO people in supply demand modelling here that, and it's been emphasised to us that 30-minute time step data is really important to you all. So this is one example of where that's been used. Okay, final case study. Any questions on that one? all quiet. That's all right. I think that case study has been presented a few times through the ESCI project, so you might have all seen that one before. This one here has not yet been presented. This is another case study I've been involved with, and it's looking at future transmission line reliability. Again, we are still in the middle of this project, so I'm going to show you the methodology, but I can't show you, even though some of the evaluation has been done, we don't have permission yet to release this, but you will see it sooner rather than later. But anyway, it's important, it's interesting to see the methodology we've taken, I think. So this is the Transgrid transmission network, and it's a network operator that's operating major high voltage electricity transmission network, mainly across New South Wales, but including other states. It includes 104 bulk supply substations and more than 13,000 kilometres of high voltage transmission lines and cables. It's very extensive. So what we want to understand, or what they want to understand, is will transmission be affected into the future with warming temperatures? So this is the context, all right? So what we're looking at is the climate sensitive decision asset / process, which is, are these lines going to be affected in warming temperatures? Now, who are our stakeholders? So in this case, it's the transmission network operators and asset managers, AEMO, because they depend on the supply that runs down these lines, and the users of the electricity, okay? So the vision and the goals is to assess the theoretical change in transmission lines static ratings due to climate change. And so in scanning for vulnerability, what we did is, the team and myself, have spoken to some designers to talk about the materials used and the pole spacing, for example. The vulnerability is the line derating under higher temperatures, maximum daily temperatures. And what they want to, they're looking at the variety of assets across the state, because all assets might be vulnerable, particularly those in areas with the greatest temperature / temperature change. So we identified these blue, these are the Bureau of Meteorology weather stations, which were identified. They use data from these weather stations currently to determine their line ratings. What they do is their summer day normal line ratings are determined using the 15th highest temperature from the last 15 years. That's how they determine their line rating, all right? So it's like a 1 in 1 year event. So it's not really extreme temperatures, like, for example, with what they were looking at with the wind farm, but this is just like it's kind of like the hottest day of the year. Okay, and how they have done that in the past is they use the daily temperature time series data from the Bureau of Meteorology observation network. So as with the first case study, we also are looking at other, so we look at what they have done in the past, but we also refer to, for example, the engineering standards and the other climate literature, other literature around regarding line ratings. So get everything you can to build a case to understand how you might undertake the assessment. So what we wanted to, so looking at the analyse climate risk step, we're now at step 3, we need to choose appropriate climate information and data sets. So we're looking, what we want to know is what the future daily maximum temperature will be, all right, that will drive this summer day normal line ratings model. Not only do we do delta scaling on gridded data sets, as you saw in that diagram that Michael showed you earlier with the 3 maps of Australia, we can actually do delta scaling on time series data sets. So in this particular case, we have got access to the Bureau of Meteorology temperature observation network daily data. And to those daily data, we can add the projected change into the time series, all right? So we add the monthly projected changes for that location into the daily, so the monthly change, projected monthly change into every January. So for example, projected January change into every daily January temperature to get a projected daily time series, okay? So this is called the delta scaled future time series, okay? So we have created, looking at the range of change, the future daily time series that resembles a similar climate variability to what we have seen in the past. In this case, we are also looking at historical. So we're comparing the historical, which is what they've been using, to two future periods. We're looking at 2050 and also 2070 for their planning, to work into their planning. All right. Again, we're looking at a range of projections into the future, and in this case, they wanted to look at it's called the maximum consensus, like where most models agree will be the change into the future. They didn't want to look at the hottest model. They wanted to look at the most likely model into the future. So we can use this, and if anyone wants any information on how to select this type of climate model, I can give you some advice later, but it's quite a simple step, but I won't show you in this demonstration today. Anyway, so you choosing the maximum consensus climate models for this case study, and the entire range. They were really interested in looking at the entire range of emissions pathways, including 2.6, because they wanted to make sure that they are looking at all of the potential outcomes into the future, as Michael showed you in those plots before. So these are 3 different climate models that were the ones that that represent where most models for that under that emission scenario is selected. And this is where most models, this sort of represents where most models agree under this climate scenario, and this Access 1 model represents where most models agree under the high emission scenario for the area of Australia that we were interested in assessing. You don't have to know all of those different details. All I'm saying to you is, again, we are looking at the range of change into the future to cover the different type of impacts that might be experienced by these transmission networks. So there's lots of ways to do these things, so which is and everyone has their own reasons for choosing the different methods, which becomes part of the discussion when you're undertaking risk assessments. So one way, or one of the in doing this modelling, or in choosing which sites to use, one thing we did look at is the potential exposure into the future of all of their different sites. So here we're using a gridded data set. This is the application ready gridded data set, similar to the one that Michael was showing in that earlier delta change modelling. So this is delta scaled using the Access model under high emissions by 2050, showing what the climate in Australia would look like under that scenario, future climate scenario. And using that output, we selected which of the different bureau sites we would use in this particular modelling study. So you can use the climate information even like to help you with decisions into the future. So here it is, where possible, quantify how assets, systems and services are likely to be impacted in future climate. It's part of how to analyse the risk. Okay. They didn't use this map to undertake their modelling, but they used it to help decide which part of Australia that they would focus on. Okay. Oh yeah, so in deciding on the data sets, we ended up deciding on that delta scaled daily data set from the Bureau of Meteorology, but we did consider trying to use the output from the probability of exceedance data set that was used in the previous study, the wind heat case study, but the probability of exceedance only gives much more rare heat events than what we were interested in. We wanted a 1 in 1 year event where the probability of exceedance, it actually represents much hotter days than what we were interested in assessing. So you do have to look around at all the different data sets to try to see what one might best suit your purpose. But the probability of exceedance was not the right data set for this case study. So, as I said, I can't show you the results from this yet because they're currently under review, but watch this space. This particular case study is going to be put out as a fact sheet for the ESCI project. Oh yeah, one last thing, and I think I've iterated it through the discussion of all these case studies is, so there's a framework, but all the time, monitor and review, communicate, consultation, like we already have our new friend Jason Lindley going to help us with our Forest Fire Danger Index first case study, because the more information, the more reliable information we can get when we're undertaking these case studies, the better. Okay, so can't stress this enough. Okay, so next thing I can talk about, are we out of time? No, we're not. Good. Shall we have any questions? I can hear someone turn a microphone on. Or is that you, Rebecca? No questions? Everyone understand what we're doing, or I've lost people? Or Michael, any comments? Have I missed something? Can you want to iterate or say something I didn't stress well enough?
All good, yep. Leanne.
Okay, cool. Jason's got a thumbs up. Thanks, Jason.
Leanne, I do have one quick question. The data set used for the transgrid, so that very final case study, can you just point that back to me? I may have missed it in the slides, or if indeed it was addressed at all.
Yeah, so I should have put it's this delta scale point location.
Okay,
it's a delta scale time series.
Great.
All right, so you can get delta scale gridded data, but you also get delta scale time series.
Okay.
So there's a few types of those time series, and one that we might be also using in the ESCI case study will be it's called the QME scale. It's a different form of scaling, but so this one was really helpful for the transgrid because it used exactly the same observation network that they were already using in their modelling. But there's other types of point location data that you can use that are not limited to these locations of Bureau networks. They can just be, they're just like at your lat long, okay? You can choose a lat long and get other time series, but they're not delta scale Bureau data. They're more like just model time series, future time series. So there's a few different types and they all suit the different risk assessments. So is that helpful?
Yeah,
go.
Yeah, Leanne, I think it's in case you didn't make it clear enough, I don't know, but
yeah, go.
So delta scaling is the simplest form, is just adding on the average, like +2 degrees, +3 degrees, whatever, and keeping everything the same. But there's actually more sophisticated versions, and this is more sophisticated, where it actually scales the extremes differently than the others, you know, to kind of really represent the kind of full complexity of the climate change signal. So it's really quite a snazzy technique. But it still retains that same advantage that it's kind of really calibrated to the observed data sets that we use for the current climate. So it's got that real advantage.
That's really helpful. Thanks.
Okay. Thanks, Christopher. Where are you based, Christopher? Are you AEMO or?
Yeah, AEMO, based in Brisbane.
Okay. Do you use daily or 30-minute or what sort of?
What do I use? Basically, some years ago, I was working in the in your Climate Change in Australia website and looking at pulling out really granular data to do some mapping and that sort of thing.
Yeah.
For some of our integrated system plan work, and just to try and understand some of the implications of increasing temperature and a range of other factors that we've pointed out today. But this ratings project that Transgrid's, you know, we'll get some information out soon as part of a fact sheet. We're going to be very interested in understanding what the implications are from this work, and perhaps how it could be extrapolated to the rest of the system.
Yeah,
and,
cool.
And the other states. So,
oh, that's good to know.
That's why I'm interested in what data was used, because maybe I can go have a look and see exactly what that looks like to see if we can do something maybe a bit similar or learn from this and do something a bit different.
Yeah, for sure. If you got any other further questions, just contact me and I can point you in the right direction as well. Okay.
Thanks.